بسم الله الرحمن الرحیم ولا حول ولا قوة الا بالله العلی العظیم. حسبنا الله و نعم الوکیل، نعم المولا و نعم النصیر. Last time we started inverse kinematic analysis for a serial manipulator. This problem is quite extensive and has many different ways of solution. We will start with very simple example, and then hopefully we will kindly extend it to some more general form. In terms of definition, last time we said that the inverse kinematic solution is the inverse path from task space variable to get the joint space variable. And this is usually solving an inverse nonlinear problem of forward kinematics when we have given the x or chi, the script x parameters or variables to find the joint variables. We call it q. We talk about solvability and existence of the solution and workspace. Said that these nonlinear equations might have no solution or might have also multiple solutions. And these two are somehow related to each other. And when this nonlinear equation has no solution, it means that the point x that we are giving is out of reach of the robot workspace. And then we can define the workspace of the robot as a reachable workspace, the place that we can, or the configuration in the space that we can reach, or the dexterous workspace, the volume of the space that the end effector can reach with all configuration. And also we define the constant orientation workspace, which is usually used for representation of a multiple degree of freedom. Now, if considering these all relations, here I start with some very intuitive and simple example, but consider it and bear it in mind that we should add up this simple example together to solve a complete problem. So it is very important to carefully understand this simple problem. The simplest possible robotic manipulator in planar case is a 2R manipulator. As you see, a 2R manipulator with L1 and L2, we can see the reach point, workspace, and so forth and so forth. So consider just a few notes about this reachable and dexterous workspace. We can see that, for example, if L1 and L2 are equal to each other, consider that we have a robotic manipulator with two lengths are the same length, and there is no limit of rotation. We have some sort of full 630 degree or 2 pi degree rotation for both joints. If this is the case, if L1 is equal to L2, then our workspace, if you look at that, if it is completely folded, we get to the origin point, and if it is open, we get to a radius L1 plus L2. So we have, or since the two are equal to each other, the workspace, the reachable workspace, is an entire disk. An entire disk with radius 2L1. What about dexterous workspace? Do we have at each point with all direction? No, there is no point except the origin. At the origin, if we just fully folded the arm, we can reach the origin with any angle that we require. So this point is somehow singular or different from the other point. And we can see that we have the dexterous workspace only at the origin. Now consider a case that L1 is greater than L2, which is like our arm. The upper arm is usually a bit longer than the lower arm. We will think about it. We will talk about it in future in the next chapter. How longer is good, and what optimized design can be seen. But in terms of workspace, which is the first basic intonation that we have in robotic manipulators, if L1 is greater than L2, and we have no, again, consider that we have no limit in the orientation, in the angular rotation of the joints, then we have a workspace, as you see here, which is a ring with the outer space. As you see, each point here can be reached by the manipulator. If it is fully extended, we have radius L1 plus L2. And if it is fully folded, we have L1 minus L2 as the workspace. It is quite intuitively can be found. And what about the dexterous workspace? The dexterous workspace is the place that we can reach with any angle, and there is no point in this. The whole workspace of the system, we can reach only with one or two angles. And it is also interesting that each point can be reached by elbow up or elbow down approach. We have two solutions for each point. Just from the geometry of the robot, we can understand that we can have such elbow up or elbow down for all points in the workspace, except the boundaries. If you look at the boundaries, it is fully extended, so there is no solution, not double solution. There's only one solution. We consider this mathematical intuition to bring some physical properties out of the system. I just mentioned it right now here, but remember this: elbow up and elbow down. And this elbow up and elbow down will converge to each other at the boundaries. So at the boundary points of the workspace, we have only one solution for the inverse kinematic problem. Either the outer ring or the inner ring, no difference. Again, we have either fully extended arm or fully folded arm. But in terms of the solution, we can see that this is some way to work with that. And this would give us some intuition how to find the boundaries of the workspace. Here I have some sort of animation that you can see how we can get the workspace. As you see, with the rotation of the angles with some grid point, you can find the total workspace of the system. Here we have some limits, and if you have the limits in the joint angle, as one of the students asked last time, then the workspace will be not the whole ring, but a portion of that. And if you just continue talking and working on that, this also shows you another way to how to find the workspace. One way is to find the boundaries. To find the boundaries of the workspace, we have to find where the double solution will reach to one single solution, if it is possible. But here you see the grid points. We give different θ1 and θ2 for the whole cases, and then we can find that how long we can reach. At this example, as you see, θ1 is limited to 30 degrees to 150 degrees, but θ2 has no limitation in the workspace, and we can continue working with that. Now, if we go ahead, if you don't mind, I just stop here. You can consider how it can finish the whole thing. We can now think about the ways, the many ways that we can find the inverse kinematic solution. And as I mentioned, since this is a very long history with inverse kinematic solution, there are so many people and papers and books written on this topic. So there is a wide range of research being done in here. Just go back, and here I can just give you some your second research I just taught about this. So we have seen two methods. One method is the grid point to find the workspace, at least the reachable workspace. And the second one regarding the boundaries to find some singular points that the two solution, the double solution will go to the single solution. There is also some other ways to do that. Especially the new ways. There is a way, I just call it here, and I would like to ask you to research on this topic and learn about it a bit more. There is a way called interval analysis. There is an analysis way or approach or a kinematic approach or an algebraic approach that can be used either for the definition of finding a workspace or a space for the robot, or also for optimality, the optimization of the robot that we will talk in next chapter. But interval analysis, there is a toolbox in a MATLAB. Interval analysis is, instead of using one point, usually we consider an interval, a segment, a line segment, and considering if this segment is in the workspace or not. If it is in the workspace, then we can elongate it. Usually we use a long interval. If one point of this is within the workspace and one point is not in the workspace, it means that the boundary is in the middle, somewhere in the middle. And then by bisection method, using the bisection method, we can make it small and small and to find the boundary of the workspace. I would like to ask you to consider reading the interval analysis, finding the right toolbox in the MATLAB, and a bit working on that to derive maybe a few examples of workspace, the 2R manipulator as the simplest one, and maybe a 3R manipulator or a SCARA robot, something else as another example. If you could do that as your research with a time limit of 1 week as we have before. So interval analysis. Look into interval analysis. Okay, let's go to the solutions. There are so many solutions, and I will give you very simple examples, and then step by step we'll go to the different approaches. Among very many approaches that are available there, I will give you maybe a method. The fifth one is very interesting. Again, successive screw. This will never end up seeing me having so physical and interesting solution. I will give it at the last section, like the forward kinematic part, hopefully in the next session. But starting with a very simple one, we can have some algebraic or trigonometric solution. They don't call it trigonometric because, you know, cosine and sine can be considered as an algebraic solution. We will see that somehow. So the first method could be just simple algebraic solution. Of course, regarding the solution, I should start from here. We could have two types of solution. One type is to find a closed form solution. To have a formulation that will give you the solution. The closed form solution is very important and very attractive because of two reasons. First, we can find the number of solutions that can exist. As you see the elbow up and down for a 2-hour manipulator, in a more sophisticated case, in an industrial robot, we can have even 16 different multiple solutions for the system. And for a more sophisticated parallel robot, this multiple solution can go to 1024 solution for one single nonlinear inverse problem. Anyways, closed form solution are in two cases better. Of course harder, but it is better. First, it gives you the number of multiple solution if you can find it, and the second, which also represents the physical concept to it. You know, we can reach a point elbow up and elbow down. And this is somehow interesting in terms of programming of a robot. And the other one, which is again very important, this inverse kinematic problem, as we will discuss it in our last chapter of this course, in the control part, and also in path planning part, are many times are used in a closed form or in a closed loop solution. So we need this inverse kinematic in the loop where we should run that with a very fast sampling time, at least 1 millisecond or 1 hertz sampling time, if you would like to implement it in a robot. And if it is a numerical solution, which is much easier to solve and obtain, the numerical solution, since it is an iterative based usually method, it takes longer than usually longer than we would like to do. Of course, the numerical solution have also many research based on this and have been worked out a lot. But since we are in the limitation of time, I don't go to the numerical solution. You can check your solution with MATLAB numerical solution. There are two functions called F0 to find one simple solution, and fsolve for one variable, and fsolve for multiple variable. And of course, sometimes this numerical solution don't converge. Now just consider the closed form solution. Also, we restrict ourselves to maximum 6 degree of freedom manipulator with primary joints, R and P joints, as we discussed here. If it is more than that, if we have redundancy, there is some other issues that should be considered. We are not at the stage to talk about that. This is more advanced. And also, if it is under actuated, we don't have enough actuator for the solution. There is some other issues coming there. I will leave them for the next chapter when we talk about the differential kinematics. But at the beginning, we consider that we have or either 2x2, 3x3, some degrees, some equations with the same number of variables, joint variables that we would like to find. The number of equation is equal to the number of variables or unknown variables to be found. And the only thing is that these these equations are nonlinear. And we are just looking for some way to find the closed form solution, to find some written solution for the inverse problem. So as I mentioned, algebraic method is the first one. analytical geometric method. I like it very much. Also, is if you use geometry, and especially analytic geometry, you can solve some not very complex, but some more sophisticated robot. Then we can go to some different solution, reduction to polynomial. It is very interesting that we can change the trigonometric problem to some polynomials, and solution of polynomials has been worked out a lot in the mathematics, and we have so many methods, especially the continuation method. There are some, these methods are given in the appendix of the books, the robotic books as well, especially in the SCI book. You can look into that. But reformulation of a trigonometric to a polynomial is very important. And then by polynomial, if you have a polynomial, of course, you can solve it by hand for a second order polynomial. And you can use the symbolic MATLAB to solve even third order, fourth order polynomial to find multiple solutions. And then you know that if you have a second order polynomial, you have two solutions for that, and this gives you also the multiple solution as well. And these two methods, the final methods, are some general methods. I give the concept of the general method for 6 degree of freedom, but special cases is used here, which we call a Pieper solution. Pieper is a scientist who has a theorem that if 3 axes of the robot are intersecting, like the wrist design that we have, UVW, or if you remember UW configuration that we used for the wrist, if these 3 robots intersect, then the solution for the 6th degree of freedom manipulator can be found. And that's why many industrial robotic manipulator have considered 3 intersecting axes in their structure. Of course, this goes back to about 25 years ago. After that, there are also some solutions for the most general 6R manipulator that can use any Denavit-Hartenberg or any screw coordinate representation. I don't go through that more general form. It is more sophisticated in the class, but will give you some intuition. You can follow that. And finally, the method of successive screw, the magic that we talked about last session, we can use that magic again for inverse solution. Anyways, now start working with that. I hope that I can at least go a few steps ahead in this session and finalize the whole chapter, hopefully next session. Consider very simple case of 3R manipulator, as you see, which we have before, RRR manipulator, and we would like to use the algebraic or the trigonometric method here. Since it is a planar robot, we can use the geometry and algebra, analytically geometry, quite extensively in here. And if the robot is not planar, we can segment it into some planar cases. Some part of it is planar. And then we can use this part of solution for the total solution there. So it is very, very important to analyze a 2R and 3R manipulator in a plane quite extensively. So the problem is, let's define the problem. So we have the loop closure method as we had before, and we have defined the kinematic or forward kinematic problem as shorthand, as I mentioned there, with 3 equations. This 3 equation we derived it several times, 2 equations for the position and 1 equation for the orientation. The problem is that the inverse. Suppose that we have this x e, y e, and theta e, or phi, and we would like to find theta 1, theta 2, or theta 3. This is the problem. And this means that how we can do that. First, the first important thing, as I mentioned, or the first important method that we use, we separate the rest and from the end effector, and we reduce the problem to the rest. And as you see here, physically it is very simple in here. Since we have x, y, and theta e, we have the cube point here. This is given to us. It is very simple to find p and just neglect this one by considering the angle phi and this length a. Very simply, if we can say px, the position, the x position of point A, P, is x e minus a3 cosine of phi. Very simple with a algebraic solution. And py is y minus a3 sine of phi. For this is very simple. Maybe for a sophisticated robot, it's not that simple. But the idea is there. We should do that to separate. What we are doing here is really, we are separating the orientation equation from the position equation. And if you consider this phi, having the phi and y here and using this equation, then we have two positions equation in which the orientation is not in here, and at the same time we have reduced the equation with three unknowns to an equation with two unknowns, theta 1 and theta 2. The theta 3 is gone because we are using only p variable, the rest variable, and we code that a lot in our forward kinematic, that usually we have 2 point p and q in the inverse in the forward kinematic. The reason is that. So simply looking at that, so if we have just this blue vector here, you can see that px and py is a function of theta 1 and theta 2. So the first step, isolation of orientation from position. And working on one of them, we work on the position now. Here we have two nonlinear equations with two unknowns, theta 1 and theta 2, which is somehow embedded in the example. The second approach is to eliminate one of these problems. If we have two equations with two unknowns, we have three equations with three unknowns, reduce it to one equation with one unknown. If we can have one equation with one unknown, if it is polynomial, it is certainly solvable. Don't worry about it. If it is even not polynomial, if it is a trigonometric, again it is possible. It is much easier to solve one equation with one unknown rather than having two equations with two unknowns, as is in here. Again, I give some physical intuition. Here it is important. If you can look into the robot, you can see that the radius here, or the length of this point, it doesn't matter what is theta. Consider that theta is changing. Theta 2 is not changing. Theta 1 is changing. Theta 1 is changing, so this blue vector is rotating here. But the length of that vector, it doesn't change. The length of this vector is not dependent on the theta 1. From this physical insight, we can eliminate that. So what does it mean? So find the length, the radius here. This can be simply done by adding the square of these two equations. Px2, Py2, we have equation, this power 2, this to power 2, and 2 times this times that. And since we have cosine here and sine here, and we add these two, we have the trigonometric relation that sine to the power 2 plus cosine to the power 2 is equal to 1, and this will be eliminated. So the first parts are very simply simplified to a to power 2, a2, a1 to power 2, a2 to power 2, but the cross correlations, a1, a2, cosine theta 1, cosine theta 1, 2, sine theta 1, sine theta 1, 2, we use the trigonometric relation here, as we call it, a trigonometric solution. We have the formulation cosine plus sine give you cosine of theta 2 minus theta 1, using that relation, instead of having theta 1 and theta 1, 2, we reduce it to only cosine of theta 2. And as you see here, this equation, it is no theta 1 in it. As we expected, we have the physical intuition that the length, which is found from the second square root of this equation, should be independent of theta 1. And by this means, the solution is done. You have now one equation with one unknown. Of course, it is still not simple. It is nonlinear. It is trigonometric. But we can find the cosine of theta. Every other things are all known. Px and py is found from here. So we can just give the known variable to one side and the unknown variable to the other side, and then find the solution. If we consider cosine of theta 2 as kappa, just to talk about it a bit more and give more analysis here. So if you have theta 2, cosine of theta 2 is equal to kappa, so we can use the kappa from just finding the known and unknown variables to ordering them and then reducing it to here. So kappa will be this one, and theta 2 will be cosine of the kappa. We have found theta 2 now. Theta 1 and theta 3 is not found yet, but theta is found. And I will come to this point again. There is some more talking and understanding and physical intuition into this kappa form as we have here. Now, look at that. We can go now to the number of solutions. So, how many solutions exist here? Cosine of theta. If we have kappa equal to something, we might have some solution. We might have one single solution. We might no solution. There is three different cases appearing here. And as I mentioned before, one of them is very important to find the border of workspace, the one that the double solution will converge to one single solution. Now, if kappa is smaller than 1, since we are using inverse cosine, if kappa is smaller than 1, so we have solution, but we have two solutions, because inverse cosine, if theta 2, suppose that, for example, 30 degree is a solution, theta star is the solution for the theta cosine of kappa, inverse of kappa, then theta 2 is equal to minus theta star is also a solution. If 30 degrees is a solution, minus 30 degrees is also a solution to the solution of cosine of kappa, inverse cosine of kappa. And this is the reason of because this is a nonlinear or a trigonometric parameter. It's not a linear parameter that have one solution. It have two solutions if kappa is equal smaller than 1. And what does it mean? This is the same old issue that I mentioned in the previous slide. It means that if we have the R here, if we have the length, we have elbow up and elbow down. Both this solution can reach to this point. If theta is the solution, here is the elbow up. Usually we use with this one, but consider that elbow down is also a solution. We can reach to the same again point with elbow down, which is theta is equal to theta minus theta star. So we have two solutions for this. What happens if kappa is equal to 1? So we have inverse cosine of 1. Inverse cosine of 1 gives a theta equal to 0 to u. This means that these two plus 0 minus 0 becomes converged to each other. So this will happen either at theta equal to 0 or theta equal to 180 degree pi. Plus pi and minus pi is also the same in this configuration as you see. And this is the border of workspace. What does it mean? This means that the L1, L2 are aligned to each other and theta is equal to 0. We have reached the outer space. As you see here, when you are fully extended arm, you have this two solution adjusting to each other, or fully folded, not only extended. If you have fully folded, if there is no restriction in theta, and we have fully folded equation, fully folded robot, again, this kappa will become equal to 1. And then we have find the border of solution. And if what happens if kappa is greater than 1? This is, as I mentioned, the cup to u, which is very far away. When we would like to find the inverse cosine of something which is greater than 1, this means that there is no solution. This point is out of space. He is elongated more than the length of the two links that we have in here. And this is, again, this is very, very interesting point, and we will come back to that. Remember, we will come back to that with some very, very intuitive and important physical properties of the robot at this special configuration. Now theta 2 is finalized. Now we go back to theta 1 and theta 3. We should find the other two parameters here. So we have this one, we reduce it into here, we eliminated theta 1 and find theta 2. Now we can go back to this equation and find theta 1, or going back to this equation and find theta 3. But let's start with theta 1. To solve for theta 1, expand the loop closure equation again. Here we have this loop closure. Now we have the theta 2. We know that we have the theta 2. We can expand it as sine, cosine, and cosine and sine. We use the sine cosine again, the trigonometric relation between cosine of theta 1, 2, or sinus of theta 1, 2 as the two parameters that we are using here. These two relations are given here, but again, now the theta 2 is known because we have found it before. So the whole parameter here is known, and only theta 1 is unknown. So we expand this equation in form of theta 1 and theta 2. Considering that theta 2 is known, we will have two equations with one unknown, but in terms of sine and cosine. We have two equations with one unknown, but we can find the cosine and sine separately, and then use tan 2 as we discussed before to find it out. This is a linear matrix equality, very simple. If you consider cosine of theta as x and sine of theta as y, so we have ax plus by is equal to something known, and cx plus dy is equal to something which is known. We have a matrix here. We use the inverse of the matrix to find x and y, which is cosine of theta and sine of theta, this is basically by the inverse of this matrix, it can be simply found. And the inverse is not a numerical inverse. We can find closed form index. We can find the delta. Delta is the determinant of this matrix, and this is the inverse of the matrix. So we have theta 1, cosine of theta 1 and cosine of theta 1 given from here, and then we can use the ATAN2, the very beloved inverse function, as we talked about it before, since ATAN2 is a 4-quadrant relation. So it can give you a relation between the solution between 0 to 330 degrees, which for cosine this is not true. We can have only 0 to pi degree, and but here we have 0 to 30 degree. Again, this part as solution, as you see, is very typical. You find it in many other problems, that by finding one solution, you can put it there and find a linear solution in terms of sine and cosine of the other angle that we can find in here. So theta 1 is fine here. Since we are using ATAN2, there would be no double solution. If we have a 2 solution as well here, then we could have 4 solutions for the general problem. But here, since we are using ATAN2, one simple solution comes from here. Now we have the theta 1 here, we have the theta 2 from the previous example, and theta 3 is very simple. We can find it from the final equation. We have phi, theta 1 and theta 2. The theta 3 will be found quite easily as before. And the solution is finished and fine, and it is closed form. Since everything is done here, you can write a program with a simple MATLAB code or in a microcontroller to give these steps of solution and find the angular value as we have in here. And still we have one particular important question to ask, which I asked you in my first research that only 10 people have replied to me. In our first research was, if you have 2 solutions, if you have some degeneracy, which one to use, which one to found. So for each position we have 2 solutions. How we should choose between these 2 solutions? The typical answer is, of course, you should use the solution which is close to your previous solution. This means that at initial point of the robot, suppose that you are at this point, at the initial point of this robot, you consider it either elbow down or elbow up. If you use it elbow down, at each second example or second point, since we are continuously moving in the space, we use the solution which is close to the previous part. So if we are elbow down, we go elbow down everywhere. If we are elbowed up, we go elbow up everywhere. And what happened when we reach to the end of workspace? If you reach to that, these 2 solutions will converge to each other. This double solution will give you one solution. Again, at that point, you should do a decision. You should have a supervisory. Now you reach to the end point, and you will be coming back. Would you like to come back elbow up or elbow down? And this is the way you program your robot. And then you can find, you choose one of the solutions. And for this case, you can see the underlying concept. Of course, for a more complicated case, you might have 8 solutions or 16 solutions for a robot, and you should choose one of them. And in the inverse kinematic problem, always when we have a trajectory, a point wise trajectory, we use the previous one to check that. And this is the way some of you have given some thought about the inverse problem in Euler angle and this degeneracy that we have in there. This is one part of that problem. Any question up to here? I can start here, give a breath, a deep breath. Almost we are done. Of course, only 1 from 5 method I have given up to now. Any questions?
I have a question.
Sure. If there is no question, then it would be somehow something wrong. Go ahead with your question.
If we have like transformation matrix for forward kinematic, why can't we use just its inverse?
This is another method. This is the first method. But we have, I told you, we have 400 different methods to use the inverse kinematic. But this is the first method. But I prefer this one rather than that. Why? Why, Zahra? Why this is more interesting than the previous one, than using some homogeneous transformation?
Is it more intuitive? Like
it is intuitive. It needs some talent. You can see and work, and it is not computer-wise. And you are not working with it 60. You know, when you have a 4x4 matrix manipulation, then you have 16 parameters. At least you have 12 equations there. Here we are talking about 2 equations, 1 equation, and then as you see, elbow up, elbow down. Robotics is not just mathematics. Robotics is the spirit of the mathematics. You have mathematics, underlying mathematics there, but you have a physical spirit to it. You can feel it, you can see it, and this gives you the feeling. You have the extended manipulated, folded manipulated. This is not easily seen in computer-wise or component-wise manipulated. Of course, this is also available. I will talk about it in a few minutes.
Also about the dexterous workspace, its mathematical meaning is like when we have infinite number of solutions.
And not only number, it should have number of solutions, but so many number of solutions. When we said that, if you look at here, volume of the space that the end effector of the robot can reach with all configuration. All configuration means if you have a theta, only one variable, theta should be from 0 to 360 degrees for all variables. Dexterity is somehow strange. So it is not just having multiple solutions, it's more than that. But keep it a while with you. I will come back with that, with very, very beautiful movies for you. Don't worry about that in next chapter, to understand the underlying concept of dexterity from the nature.
Okay, thank you.
Hossein, you have also a question. Please quick, because I would like to go to the next part.
Good morning.
Good morning.
I have one question, please. According to your experience, you talked about supervision of the position. In the presence of new technology in processing and control, how much do we suffer from singularities if the system is supervised and controlled, respectively, with previous angles of solution?
The suffer is always there. The burden is always there. But you should work out somehow. And the way I'm using a supervisor, could you please turn off your microphone when you are not speaking, because my speech is... when you have a supervisory loop, you have some decision. And this supervisory, as I mentioned, could be quite classic, very, very intuitive, as I mentioned, very simple. Just look at the previous example or previous point. It could be also quite artificial, intelligent based. You could have some more knowledge to use that. You can have deep learning methods to use the supervisory loop. You can have many, you can use fuzzy systems for supervisory loop. Of course, not for just this simple case. This simple case doesn't need that much effort. But I remember the saying of one of my professors that to kill a mosquito, you don't need an atomic bomb. To kill a mosquito, you can have a simple supervisory loop. But if this mosquito becomes larger and larger, then you need maybe some more sophisticated case. But it is quite possible to do that. And it is not possible, it is necessary usually to do that. I hope I have answered your question. Let me go to another part. Now that we have the trigonometric solution, let's go to geometric solution. What would be the geometric solution? It's very similar to that, but it is a bit simpler. If we use, if simpler in terms of arithmetic, harder in terms of concept and your intuition. It needs more talent or more, smartness to do that. But the solution will be much smaller. Instead of going through this, let me first of all say when it will be available. This is very general. I cannot prove this, but when you have a spatial robot, if the Navier-Hartenberg parameters alpha I that we discussed there, the twist angles are either 0 or plus minus pi. If we have only the twist angles, either 0, no twist angle, or just perpendicular, in many examples that we see in industrial application, this case is considering. And maybe this is because to make the inverse kinematic problem easier. But in some cases, we have some angles. In that case, it is not. But what is not possible? The way we are doing, we have a spatial kinematic. We can reduce this spatial transformation into a number of planar cases. We are working only on the 2R or 3R manipulator in a plane, but consider that this robot has a base, that the base is also moving, and has a wrist that the wrist is also moving. If these angles are either 0 or plus minus pi over 2, so we can separate the problem or isolate the problem into some planar cases, and then we can use this planar case that the solution that I gave you here many times again in this case. And if we have this, then we can use the analytic geometry here. If you remember the analytic geometry, if you have a triangle, very simple. If you have a triangle, we have the cosine formulation for that. The cosine formulation gives you that this length is equal to this length in the squared, which is x plus y squared. I just make it very simple. X plus y squared would be L1 squared, L2 squared, minus 2L1, L2 cosine of this angle, minus cosine of 180 degree minus theta 2 angle. Of course, this triangle and this triangle give you the same solution here. I don't use the beta and theta gamma here. I just use the theta 2 and the cosine angle in one simple formulation in analytic geometry. And this is exactly, if you consider cosine of theta 180 degree minus theta 2, which is equal to minus C2, this is exactly the solution that we have worked out here with a number of steps to reach to this point. Here you can just go with just simple touch and use the cosine angle. There are some other geometric approach here. And it is interesting, as Zahra has worked out before, we have this geometry not only for planar case, we have spherical geometric as well. We have, if we are working on a sphere, then we have spherical trigonometry and spherical geometry to be used for that kind of robot. And there is so many books in here. Yesterday, I was looking into my books. One of a very old book from Professor Angeles I got. It was on spatial kinematics. And it is so many issues in that book that can be considered in here. Anyways, you can find this, and the solution goes exactly the same way. You find one of the parameters, as I mentioned. You have a larger problem. You put it into a smaller problem, which is a planar case. Then you make it a simple triangle or something that the geometry can be used from analytical approach of some geometry. You can find the solution as we have done is for here. I'll go to the next part, which is very, very important. I can say this is more general. This one is the previous version that I said is very good in the exams. If you have an exam with short time of solution to give the solution, the smarter you think, the faster you get the solution. Of course, we don't have that difficult example in my class, so don't worry about the exam, but it is good to just refurbish and you use your smartness and intelligence in the solution. But this approach is, sorry, is very, very common. Go ahead. Go ahead.
In geometric approach, the formulation that is used looks very general. Why it only works when alpha I is 0 or pi over 2?
This is another thing. It says that if this goes to this question, decompose the spatial geometry to a number of plane geometry. In order to decompose the spatial geometry to a number of plane geometry and then use this plane geometry approach or geometric analytical approach, this is a restriction. Not a restriction, this is usually used to have that. If the angles are not equal to 0 or pi over 2, then you cannot decompose. These two will go into intervening to each other. Then you cannot have a simple planar case. You should work with spatial geometry, and the spatial geometry is, of course, harder. If you know some spatial geometry approach, that can be also used quite well. But if you want to decompose it into plane geometry.
Thank you. By the way, your sound is a little bit decreased. I think your microphone is
Yes, because I just had some. All right, you have my voice, yeah? Perfect. All right, now let's go to this approach, use of half-angle tangent relation. I like it very much, and I've used it a lot in many, many examples, and you will use it a lot. This means that to replace or to convert the trigonometric equation into polynomials, and when you have polynomial, believe me, there are so many work on solving a high-order polynomial case. I have seen that you can solve a polynomial with degree 16, 32, even higher. Not every polynomial. With some cases, you can find the solution. Remember, not numerical solution, analytic solution for that. And if you have a polynomial base, it is much easier to use F0 function also in MATLAB, or finding the numerical solution is much easier if you have basically the polynomial equation instead of having trigonometric. And how we can do that? Very simple. I don't use X here just to distinguish between the position that you have and this parameter. So that if the half-angle tangent relation, if you use tangent of theta, half of theta as a new variable, then cosine of theta can be seen as a very simple case in 1 minus u2 u squared over 1 plus u squared, and sine of theta is 2u over 1 plus u squared. And this is usually the case. I give some enthusiasm or some, explanation to a high school student that learn this relation and don't know when they are using them. You can use a lot of this relation in robotics. There are a lot of mathematics that you have in your background. Do you remember 2u over 1 plus u squared? If you go back to your high school relation and also in mathematics 1 and 2, these are very, very useful relation. And the u is tangent of half angle tangent, actually, theta over half of theta angle. Now, how we can use it? Let me give you an example. This is not this for a robotic. You can for any general method. You have, for example, a cosine theta plus b sine theta is equals to c. So you have one equation, one unknown, but it is trigonometric. Just using, instead of cosine and sine, put these two relation here, and then you come up with a polynomial solution. Very simple. You don't need to do the linearization that we did before. You have a matrix and find the delta. The same result will find it here, but if you have sine and cosine here, you just put the these two relation here, and then you write it into a polynomial version here. As you see, the polynomial u squared minus 2bu plus something is equal to 0. We have a second order polynomial. We have two solutions for that. Of course, this part should be positive to have solution, and this gives you the exactly as I mentioned, the three part. You have either two solution, elbow up, elbow down. You can have the adjacent or the converging these two solution to one solution. This gives you the singular point or the borderline. And if it is out of that, if this is negative, then there is no solution. There is out of the workspace. So by this quadratic polynomial solution, you can find the theta. And when you have u, then you can use tangent, arctangent. Of course, theta over 2 is tangent of u. You can find the theta variable here. We prefer, as much as we can, to use arctan2 instead of arctangent. But inverse kinematic problems are so difficult that if you find a solution, either if it is arc cosine or arc sine, you will ease up that thing. But if you look at the professional ways, usually we use the equation to come up with some arctan2 equation that we have a 4-quadrant solution. And that's the final part. We will see that in the future examples. So consider these three methods, the basic method, either algebraic or some geometric, or considering reformulating it into polynomial. Now we can go to some real problem. Of course, from now up to end of the class, not this, the end of semester, I can just talk about inverse kinematic. And the methods are available there. But I'd avoid doing that. And I don't want you just to be a kinematic person. I would like you to be a roboticist with more knowledge on controls. So I will just move on two more general ways and then give you some examples to look into that. The one example that you see now, we are going to 6 degree of freedom robot. There is no planar case. This is no simple equation that we can find as in a geometric ways. We should use embedded or a combined method of solution to find the inverse kinematic. Now, what Peppers says, it goes back maybe to maybe 35 years ago or something about that. it says that when three axes intersect, the concept is like that, very simple. When three axes intersect, three consecutive axes intersect, then we can decompose the position and orientation, or decompose the six equation into two decoupled three equations. Still, it is very hard to use to solve the three equation itself. You should use the previous one. But this is much simpler than you solving a 6 by 6 equation, 6 equation, 6 unknown. So if we can decompose the problem and we can reduce the problem to one equation, one unknown, then it can be solved quite easily. Pieper gives you this equation, and I give you the method that it will generate that for you with a general Denavit-Hartenberg problem, or a general 6R manipulator. It doesn't really restrict that to a case. It doesn't leave me, you know. To show you how this works, I use the general industrial robot that we have three axes. The wrist position has three axes of rotation, and these three axes of rotation are usually intersecting each other, as you saw in our previous examples, many examples that we gave in forward kinematics. So this means that the frame 4, 5, and 6, the last three frames, which gives the orientation basically of the manipulators, are intersecting. So this means we can make the position and orientation, separate them by using the wrist point, W, or P point. We call it P in the previous example, but we call it W in a general case. So we find the reach point, the position of the wrist point. This position doesn't really include the last intersecting angles, theta 3, 4, theta 4, 5, 6, and only is dependent on theta 1, 2, 3 if it is a 6 degree of freedom, especially R manipulator. Then we have the Q1, Q2, Q3. We can find the position, and then when we have this three position, we can go through the orientation of the end effector. How to do that? The general way is written here. Of course, we should do some example. I give the general method here, and then in the next session, I will go through some examples. Here you see that we say, okay, if this is the intersecting point, my wrist is important. We call it O4. The point of intersection, origin of the frame 4, 5, 6 are all the same. So PO4 with respect to 0, the position of this is equal to the position. We can find the position in terms of these consecutive terms, as Zahra told us. Why we don't use the homogeneous transformation? Yes, we use them if we are obliged to, if we have no other way to get rid of them, of course. But we use them, you know, there is no other way to do that. So what does that mean? This is very simple. PO4 with respect to 3 can be seen, since this is a point of a robot. If we have a general robot, you know, with A eyes and D eyes and alpha eyes, everything general, then we can see that PO, this wrist, has a length and offset D and a twist angle alpha with the Denavit-Hartenberg convention. Here I'm using the Craig convention, since we are using the Craig. Of course, you can use the Paul convention as well. It doesn't really matter, you know. Here you can see there are some fixed parameters here given relating the problem of the geometry of the robot, and this multiplied by these three angles, we have the Q1, Q2, Q3 angles in here. This gives us the position, and we try to solve that position quite simply. How we can do that? Of course, we should use the general Denovi-Hartenberg transformation, theta 1, theta 2, theta 3 for general cases, and find that. Of course, for any special example, the equation you find is much simpler because you don't have all AI, alpha I, everything all non-zero. Many of them are either 0 or pi over 2, and reduce the problem to a simpler case. But consider the most general one here. As you said, the most general case, now we can see that this, combining this 3 by that, we can just multiply that using symbolic manipulation. We have very, very long equation. As you see, G1, G2, G3 will be seen in here with, this is decomposed in some way that we can find the theta 1, theta 2, theta 3. G1, G2, G3, there are long equation, and in which just the F1 is also a long equation. F2 is another longer equation. So for a general case, this equation is quite long, but we just put it in a form that we can manipulate with it. So we can see that this can be done. Just believe me, and you know, this is not a claim, this is a proof that has been done by people. So you can do that, and then now we would like to solve this equation for Px, Py, Pz of the risk manipulator. Considering that F1 is a function of, as you see, theta 3, F2 is a function of theta 3, again, as you see, with some parameters, and F3 the same way, while G1 is a function of theta 2, G2, theta 2, and theta 3. We have decomposed this two to have further decomposition, and theta 1 is coming here. So this function is a function of theta 1, theta 2, theta 3. Theta 3 is more involved because it comes into all the relations, but theta 1 and theta 2 are less involved. Now we would like to solve the problem. We start again with the same idea we used in before. Using the length, the blue vector, the blue line I showed you in the 3R, we use the length, we call it R. This is exactly as we used in here, this length, or in here, this length. Here we use the length, but in a, not a planar case, in a more sophisticated spatial case. G1, G2, G3 to power 2 gives you R or R squared, it doesn't really matter, which this is all of them all together. And you have a hectic, long parameter system here. But we can write this equation along the Z component. This will make it easy. As you see here, the Z component is much easier. These two have S1 and S2 is depending on theta 1, theta 2, and theta 3. But this equation doesn't include theta 1. And that makes the life much easier. Not only using the whole thing, we call the Z component as well. So we have three components here. The Z component are written here, and as you see, the Z component is much simpler in here. Now, again, here we have K1, K2, K3, that as you see, the K3 is very long, K4 is long, but K1 and K2 are rather simple. Not simple, but rather simple. We have F1 and F2 in here. So we have the theta 3 considering in here. Now we eliminate theta 1 and find the theta 2. And if we can eliminate theta 2, then we can solve for theta 3. In this equation, theta 1 is eliminated, this one, and is of simple form of theta 2. Now solve for theta 3. Now we have theta 2 and theta 3 here. We should eliminate one of them. Again, this is in most general form very hard, but if there are some simple cases which are usually used in the industrial robots, says that if A1 is equal to 0, then look at here, if A1 is equal to 0, R is equal to K3. R is known, K3 is a function of F, you see, is a function of theta 3. And it is a very long version of theta 3, but you can use the polynomial in the half tangent relation to make it a polynomial and solve for that. Look at the concept instead of the details. If A1 is 0, then this equation is solvable. Quite easily you can find theta 3 by tangent half square, as I mentioned before. But usually A1 is not 0. This is, a robot with length 0. We have some problem here. But if S alpha is equal to 0, this is much more happening. When sine of alpha 1 is equal to 0, it means that alpha is equal to 0 or 180 degrees. This is more happening. Then you look at this one. This equation becomes Z is equal to K4, and K4 is also very simple. And Z is also very simple. This is much simpler than this equation. And that can be also solved very easily for theta 3. Of course, you should write it and see it, and for any particular robot, you have alpha 1 and everything to do that. And now you can see how Pieper has done. Pieper has solved not just with one robot. It says that any robot that has 3 intersecting points. You can see that this can be solved from this equation, and then we can find theta 3. If this is not the case, then we are in the trouble. Then the problem is really long, but we have another ways. This is otherwise. If it is not 0, then we are in a trouble, but we can eliminate S2 and C2 by the same way we used in the previous case. From this equation, as you see, we have S1, you see S2, C2 and S2, S2 and C2. We have 2 equations, 2 unknown. This is, with respect to S2, is linear. We use the matrix form, use the inverse, and solve this problem. Of course, the problem has a long version of cosine, as we see in F terms in here, but you can usually use this way by this means. And by this means, this can be found quite easily. When we have theta 3, then we should go for theta 2 and theta 1. And that would complete the solution. Let me stop here and give you some time. Now you understand the meaning of inverse kinematic solution. Inverse kinematic solution meaning working with this very long equations in a closed form way, not in a numerical approach. Thank you. If there is any question, please. Hopefully no question, and I wish you health and prosperity and more time to think about these mathematical problems in more details. Goodbye until next session.